Welcome everyone. This video demonstrates the Pedestrian project, an open call 2 project of 6G-BRICKS. The project is carried out by Nextworks and the CNIT research unit of the University of Modena and Reggio Emilia. The main objective of Pedestrian is to protect vulnerable road users by predicting their future trajectories on the road. This is done by using privacy-preserving techniques so that road data are never shared across the network. The solution leverages cooperative, connected and automated mobility to allow vehicles and roadside units to collaboratively train AI models. The scope of the project directly aligns with the European Union Vision Zero to eliminate road fatalities and serious injuries by 2015. In this, connected vehicles are equipped with transformer architecture to predict pedestrian trajectories, and federated learning is used to enable distributed learning between vehicles and roadside units. Moreover, hierarchies are established, extending federated learning to hierarchical federated learning, enabling a multi-federation scenario, in which connected vehicles can switch federations based on their mobility events. The project makes use of the 6G-BRICKS Evercom testbed to validate the pedestrian solution from a network perspective. The testbed provides the possibility to model complex network scenarios via the deployment of both emulated user equipment and core network and run application. Moreover, it allows the possibility to deploy virtualized application over the map, and from an experimentation perspective, it enables the collection of real-world network metrics and specific KPIs. Overall, the project makes use of 3 different testbeds. In the Nextworks testbed, federated learning and hierarchical federated learning scenarios are tested using an F emulator for mobility events, and resource-intensive AI workloads are outsourced to the CNIT Polito testbed. Finally, network traces collected in the Nextworks testbed are used as input in the 6G-BRICKS Evercom testbed, where network measurement and KPIs are collected. In this example, a hierarchical federated learning experiment is started with 1 root server, 2 hybrid servers, and 4 leaf nodes. The root server starts its root aggregators and pulls the available clients, the hybrid servers. The hybrid servers receives the training request and starts their aggregation servers, pulling the available leaf nodes. Then, the leaf node receives the request, perform the training and send back the results, which are aggregated first at the hybrid server level and then at the root server level. This hierarchical federated learning process is carried out for a predefined set of rounds. All the aggregated models, roots and hybrids are stored in MLflow model registry, where also all the experiment metrics are stored for each node, root, hybrid and leaf. This enables observability of the experiments and the storage of models that are then deployed in the connected vehicles and roadside units to enable the prediction of pedestrian trajectories. The network traces between the root servers, hybrid servers and leaf nodes are collected and stored for each round of training. These are then used in the 6G-BRICKS experimentation testbed as input to validate the pedestrian solution from a network perspective. The testbed provides the possibility to deploy core network and run application. The feature used to test the pedestrian framework is the traffic generation tool, which enables to deploy user equipments and use them to simulate traffic in a realistic 5G environment. The previously collected network traces are used as input for traffic emulation using the deployed user equipments. The experimentation API returns network statistics for each of the user equipment. As soon as the experiment finishes, network measurements are retrieved and used to compute network KPIs. In this, statistics about downlink and uplink of the different entities can be separately checked, and network KPIs are derived from these statistics to validate the feasibility of the pedestrian solution in a 5G environment. As results, the combination of transformer networks with federated and hierarchical federated learning successfully enabled real-time, privacy-preserving trajectory prediction while minimizing the bandwidth consumption at the edge. Validation of the solution on the 6G-BRICKS Ericon platform proved the system feasibility in a 5G environment, meeting core KPIs for network efficiency, latency, and training performance. Future deployments will prioritize advanced weighted aggregation strategy and personalized federated layer to better handle the non-independently and identically distributed data challenges to improve the transformer network prediction accuracy. All the results and material are available on the Pedestrian GitLab project. Thank you for your attention.